Hi everyone, my name is Javier Fullea. I'm a candidate professor at Universidad Complutense in Madrid in Spain. And I'd like to show you what we've been doing within inner space. This is the work that I've been doing with my student Carlos, and also in close collaboration with Sergey's group. Actually, his talk is very nice because it introduces naturally what I'm going to be showing. Unfortunately, I have to say that the study case that I'm going to be showing is not US, it's Africa. This is coming next, but hopefully it will give you an idea of the method. So the primary goal of what we're doing is to try to understand the role of the lithosphere as a heat source, essentially. So trying to make geophysically informed predictions on the surface heat flow and the temperature distribution in the best possible way. In the case of Africa, if you see in the left plot, this is the data that we have, surface heat flow measurements. And it's actually part of inner space as well. This is the quality control database by Sven's group. You can see that in some areas the coverage is pretty good, but in some other areas we practically have nothing. We need to extrapolate this in some way. There are different approaches as to how to handle this problem. For instance, here I'm showing you a couple of examples which are based on like data-driven approaches, machine learning of different sorts. The underlying idea is to take measurements of surface heat flow and other observations that can be related to some extent to heat flow, and then apply machine learning techniques to extrapolate. As you can see, the maps are similar in the long wavelength features, but then at the intermediate and small scale, well, things are not. There are differences, of course. Our approach, on the other hand, is, as Sergey pointed out, model-driven. We want to understand and determine in the best possible way the geotherm, the distribution of the temperature within the lithosphere, and therefore the surface heat flow as well. And we know that there are four main factors, as Sergey mentioned, that control this: the thermal thickness of the lithosphere. So that's the point where the geotherm turns from conductive to convective. That's an important one, and we can do a good job with surface waves. The amount of radiogenic heat production in the crust, mostly in the crust, the value of the thermal conductivity and the crust and the sediments, and because of the two points above, well, the thickness of the crust. So, to train the thermal lithospheric structure of the thermal thickness of the lithosphere, surface waves are uniquely suited. These are mostly sensitive to precisely the depth range that we are interested in here. And so when you hear an example, state-of-the-art wave velocity map at 150 kilometers, velocity anomaly. So if you plot that on top of well-known thermal anomalies, you can see that there's a very, very good correspondence, which is why this is one of the data sets that went into the favorability map. However, as Sergey mentioned, this is not trivial at all to convert a seismic velocity anomaly model into temperature. There are different things that make the choice non-unique. So what we do is to take a step aside and compute phase velocity maps or dispersion curves, as the one that you see here, which are related to a specific point within the Earth. These contain equivalent information to the tomography model, but have the advantage that can be modeled in 1D. This is exactly what we want to do, model different 1D films across the region of interest. So the modeling that we apply, we call integrated geophysical petroleum model approach, mostly surface wave and surface heat flow, other data sets as well. And simplifying the main idea, you could think of it as a tomographic inversion for surface waves, where the main parameters wouldn't be the seismic velocities and the densities, but instead temperature within the lithosphere and the sublithosphere, mantle composition, crustal lithology, these sort of things. So without, again, going into much detail, but we parameterize a 3-layered crust, or 4-layer, depending on whether you include sediments or not, where the main parameters will be seismic velocities and densities, which are lithologically linked. And then in the mantle, the main parameter would be the thermal thickness of the lithosphere, particular isotherm that we choose, and the controls to a large extent the heat flow. And then, well, some of the parameters describing the temperature below, but maybe not so relevant. They're relevant because they control how you fit the whole curve. But for now, the important bit for us is the depth of this change in the slope. Importantly, also, we compute seismic velocities and densities as a function of temperature, pressure, and composition using a thermodynamic formalism and different databases. And this narrows down the inherent non-uniqueness of the possible seismic models that you can get to fit the data equally well. So, as I mentioned, we've been working on that for some time now, in different regions across the world. So when you hear an example of a recent geothermal project in Ireland in which Sergey and I were involved, or are still involved, so we applied integrated inversion of surface wave data from local seismic arrays, and we also did some benchmarking, or they have to take few, unfortunately, boreholes available. And what we saw actually is that whenever we played a bit with thermal conductivity of the topmost layer, actually using reported values, we got a very good fit to our otherwise completely independent estimate of the temperature. Good validation. So for inner space, we produced a preliminary model of the temperature structure in Africa. This is constrained by surface wave velocity map, state of the art from Sergey's group. We also use as the input, although we produce it as an output as well, but we can read as an input surface heat flow with some large uncertainty bars, because for instance, keep in mind this model that we use here from Lucas 2019 is away from the measurements, it's also prediction, it's a model. And also we need some input average temperature at the surface, which we took from this work. And this preliminary model, in terms of the crustal parameters of relevance, thermal conductivity and heat production, is relatively simple. It varies vertically, at least for thermal conductivity, but is laterally constant. And in particular, for the radiogenic heat production is constant at 0.9 microwatts per cubic meter. We also use as prior information the wave velocity from the well-known CRAS 2.0 model. Here you see some of the outputs for this model. On the left, you can see the thickness of the lithosphere or Moho depth. On the right, you can see the thermal thickness of the lithosphere. For a comparison, I've included a couple of geological outputs from inner space, coastal faces and faults, and the igneous faces here. So you can see that, particularly looking at the lithospheric structure, there's a very good correspondence between some of the units. This all went into the GeoMap, of course, it's freely available. We also produce a temperature estimate, of course, as the main product. In particular, here, this plot here, you can see the predicted surface heat flow from our lithospheric model and the temperature at 2 kilometers depth, at any depth, really, but in this case, it's 2 kilometers. And for a comparison on the left, I'm including the initial starting surface heat flow model. You can see that we capture the same long wavelength features or structures, but our map is much more simplified, of course, as one would expect, because we are solving for, the heat conduction equation controlled by basically lithospheric thickness, and we are killing mostly the complexity, the lateral complexity in the crust in terms of heat production and thermal conductivity. We did different tests for different values of the crustal heat production. This is 0.9 microwatts per cubic meter at the initial model. And we also tested 0.6 microwatts per cubic meter, which could be more similar to what you expect in cratonic regions. And of course, in this case, in cratons, you get predictions of surface heat flow values that are closer to measurements, but then again, the values are too low in other regions, which means that, of course, we have to move towards a laterally varying crustal model, which we did. This is what we're doing, updating the model using a variable heat production and thermal conductivity. And in particular, we focused only on columns or regions where we have high quality surface heat flow thermal conductivity mappa data. That's from basically what Sven Fuchs presented, the quality control database, surface heat flow thermal conductivity, either measured or inferred from surface heat flow and temperature gradient. And then we also use another output from InnoSpace, which is the detailed updated sedimentary thickness map from Megan and collaborators in Cambridge. We have a separate layer with different properties for the sediments as opposed to the crystalline basement. And then we can, well, first we have to upscale to make it merge or comparable at least with the surface wave data that we are using at this stage. That's the circle, that's the sort of resolution that we have. And here we are only inverting for columns where we actually have reliable surface heat flow and thermal conductivity values, which you can see here on the right. In this case, we do have an as part of the inversion prediction for the radiogenic heat production, which we separate into the upper crust and sediments, where we strictly invert for it, and then the mid and lower crust, where we indirectly invert. We basically invert for VPVS ratio or lithology, if you want. And then from here, some relationships that we derive, we calculate the heat production. And then on the right, you can see the temperature at 2 kilometers in this case, which is, of course, different from the earlier model with constant thermal conductivity. Finally, to wrap up, because, of course, this is all about US, just wanted to show the methodology. We've produced a new integrated geophysical, petrological, and lithological lithospheric thermal model in Africa, essentially constrained by high-quality surface wave tomography and surface heat flow data. And because of this, we can make a prediction of the lithospheric scale surface heat flow, ignoring effects like advection and other things perturbing really like the lithospheric contribution to the surface heat flow and also the shallow temperatures. And as work in progress, we are trying to calibrate the integrated inversions with high quality surface heat flow measurements, thermal conductivity, sedimentary thickness. And of course, the next step would be to laterally extrapolate the properties that we are getting for those columns with some geological sense. This we are doing in collaboration with the geologists within InnoSpace group, and also obviously to export the methodology to other continents. And in this regard, North America is the next in the line. So yeah, that's all. Thank you.